Hello everyone, my name is Bill Brown and I am the Sales Division Manager here at Hosokawa Micron Powder Systems. We at Hosokawa Micron Powder Systems welcome you and thank you for attending our webinar, Low Shear Batch Mixing. Let me point out, if you have any questions during this presentation, you may submit your question online at any time. Please refer to the Q&A pane on the side of your screen. At the conclusion of this webinar, we will try to accommodate all of your questions during this Q&A session. Hosokawa Micron Corporation is the global leader in powder processing equipment and systems with headquarters in Osaka, Japan. With a global workforce of nearly 2,000 employees, we have production facilities in 5 countries with 12 technical centers and research facilities. Hosokawa Micron Powder Systems was founded in 1923 under the name of pulverizing machinery. We design, manufacture, and assemble equipment for size reduction, classification, mixing, containment and isolation, compaction, and laboratory analysis. Our equipment is designed for chemical, food, pharmaceutical, minerals, nuclear, cosmetics, and the plastics industries. Here in Summit, we have a research and testing facility, complete with an analytical laboratory. And we encourage our customers to participate in equipment trials and system evaluations. At this time, I would like to introduce our presenter, Mr. Chris Paulsworth, our in-house expert on mixing and drying technologies.
Hello, everyone, and thank you for the kind introduction, Bill. I'd like to welcome everyone to today's webinar, Low Shear Batch Mixing Technology. Today we'll be discussing the basics of powder mixing with principles and considerations. We'll examine the benefits and limitations of low shear homogenization. We'll discuss the operation of 3 types of mixers and then compare the 3 types of mixers for the powder mixing process. At the end, we will have a question and answer session. So to begin, there's many types of mixers. There's a lot of types of mixers for liquids, for foods, for all different kinds of various products. Today we're only going to be discussing mixers for powders, and we're going to focus on low shear mixing and batch mixing within that specialty. So to get started, why low shear mixing? Low shear mixing is good for a lot of reasons, but really what it's good for is free-flowing products, fragile products, and heat-sensitive products. So if you have a product that needs very gentle handling or is not able to be subject to a lot of heat or mechanical stress, these are the types of reasons why you would choose low shear mixing. So if you look at mixing as a whole, you can select based on a wide variety of mixers. We tend to divide powders based on their cohesiveness. So you have free-flowing powders on one side and cohesive powders on the other. And for free-flowing powders, you're going to select different types of mixers. And then as your powders get more cohesive, or your mixture gets more cohesive, you're going to select a different type of powder. So roughly speaking, we divide them into low shear, mid-shear, high shear, impact, and particle modification. Low shear is going to be more of an ordered type of mixer. So you're going to have, the mixer is going to be at a low speed and your particles are going to move in a nice orderly fashion throughout your mixer to give you your mixing. For mid-shear, you're going to be at a little bit higher energy, a little bit less orderly, more random inside the mixer. For high shear, what you're going to do is you're really going to put a lot more energy into the mixture and you're going to be shearing those particles against each other or against the wall to get your mixing. For impact mixing, what you do is you disperse your particles in air and you impact them with a rotor, and that's going to break those particles apart and allow them to mix freely. For particle modification, what it is it's a form of high shear mixing, but taken to the next level where you really put a lot more energy in. So today we're going to be discussing low shear. So we will start with free-flowing powders. So looking at free-flowing powders, how do you identify a free-flowing powder? Well, free-flowing powders have low inner particle forces. They tend to have a particle size that's above 75 microns. It can be below that too, and this is really just a general guideline. They tend to have low moisture content. You don't want any moisture in your batch to stick those particles together, with the capillary forces. They tend to have a low aspect ratio. If you have particles that have a high aspect ratio, they can kind of mat together and stick together and can be a little bit harder to mix. A good indication of this is the angle of repose. It's a calculation where you take your powder and you drop it onto a plate and you measure the angle of the peak or the mountain that it forms. The steeper the mountain, or the taller the mountain, the steeper the angle of repose, and the more cohesive your powder is going to be. And one good example of this is going to be sand. When sand is a dry sand, you can hold it in your hand and it will flow through your fingers freely. So you have low interparticle forces, and the gravity takes hold, and it just allows that particle to flow out of your hand. If you have wet sand, the water is binding your particles together. You have a cohesive powder, and that's going to be a lot harder to mix. You have to really break those forces that are holding the particles together. So with free-flowing powders, there's certain problems that you have to overcome, and that one of the main problems is segregation can and will occur. What segregation is you are trying to mix your two powders together or your multiple powders together, and those powders will naturally tend to separate. So what happens is, say you have your powder in a vessel and you have multiple powders. You shake your vessel, you have vibration. You're going to have your coarser particles or your particles that are lighter, less dense. They're going to migrate to the top of the batch. And then at the same time, that kind of goes along with percolation, which is really just where your finer particles will naturally shrink down to the bottom of the batch, or the bottom of the batch. They will migrate through, and you'll end up with a higher amount of those finer particles in the bottom. For transportation, what can happen is if you have your powder and it's falling out of a spout, the coarser particles have a higher mobility. So as they hit the pile of powder, they will migrate out towards the outside, and you can end up with fines in the middle. And then if you are air conveying your powders, what can happen is that the coarser particles will actually convey further. So if you were, say, filling a hopper and you have your particles coming in by air convey, your fines can end up on one side and your coarse can end up on the other side of the hopper. So we're going to talk about mixing, but there is an entire step above mixing when you consider your process. So you have to consider everything that's going to be going on around your batch, feeding your batch, discharging your batch, special characteristics for your powder if it's highly toxic. If you are mixing, say, a very small amount of one powder and a very large amount of another, or if you need to have a reaction occur, or you are trying to avoid product degradation, all of these are also things to consider, not just is your powder free-flowing or cohesive, or things along those lines that we'll discuss. So really, when you look at a mixer, you should consider this, but also you should look at your entire process. And then it's going to be an interplay of your process, the mixer, and that's going to give you your mixing time. So to get started, free-flowing powder mixtures. What this slide shows is you have particle A on the one side and particle B on the other side. So you have a totally segregated batch. When you mix, what you do is you take those powders, you randomize them together, and you end up with random mixing. Note that this is not completely ordered. This is totally random. So how does it work? What you're doing is you're taking powders from a portion of one batch and moving it to a portion of the other batch, and then shifting those places around to give you a particle that used to be next to all of its own kind of particle, and putting it next to the other type of particle, and so forth, until you end up with a totally mixed batch. So really, the thing to consider here is that you're transporting the particles around within the batch, and that's what's going to be doing your mixing. So when we discuss transport, there's two main transport modes that we'll be considering. One is diffusion, the other is convection. Diffusion is more of a randomized transport where you allow the particles to randomly move, assisted by gravity, but mostly on their own, and they will spread out and diffuse among the other particles, and that's going to give you your mixing. The other is a more deliberate form of transport, and that's convection. So what we're going to do is deliberately generate specific flow patterns or currents within the batch. And that's what's going to be taking your powders from one portion of the batch and moving it to the other portion of the batch. And that's what's going to be generating your mixing. So those are the two types of transport that we'll be considering. And that's also the two main categories of mixers that we'll be discussing today. So how do you select between a diffusion mixer and a convection mixer? So just in general, diffusions tend to be cheaper and easier to maintain. They are, because of this, they're the default. So if you can, you would use a diffusion mixer. But there's a large caveat, and that is if your mixture is segregative, it cannot be mixed using diffusion mixers. So if you have a large difference in particle size or a large difference in bulk density of your products that are being mixed, you cannot use a diffusion mixture. What will happen is, if you remember a few slides ago, we had discussed the segregation that will occur. This is what will happen if you try to use the diffusion mixer. You'll end up with a segregated product, and it won't be mixed. So our first type of diffusion mixer that we'll be discussing is the tumble mixer, also called the tumble blender. I'll use mixer and blender interchangeably during this presentation, so just consider them to be the same word. So what the tumble blender is it's a hollow vessel, and you fill it partially with powder, and then you rotate it slowly on an axis. So you are going to rotate it slowly on the axis, and the vessel is going to be lifted up by the friction against the wall, and it's going to cascade or fall down onto the bulk of the product. As it cascades or as it falls down, it's going to diffuse across that top surface. So you're taking that one portion all the way at the top of the wall and spreading it out across that whole batch, and that's what's going to be doing your mixing. So you're taking one portion of the batch and you're kind of dispersing it amongst the rest of the batch, and then you cover that with fresh material, and that's what's really going to be doing your mixing. If you look at these slides, what they're talking about, or excuse me, these pictures on this slide, what they're talking about is the speed of the blender. So as it rotates, you need to select the correct rotational speed. You can rotate it so enough where the powder will just fall down onto the batch. You can rotate it such that it will lift up and then cascade down, but then you can also rotate it so fast that the material won't fall down at all. Really what's happening is you're not allowing gravity to work. The force that the blender is putting into the powder is so high that it's overcoming gravity, and you're not going to do any mixing at all in that case. So you want to avoid that case. So why would you choose a tumble blender? Tumble blenders, are simple. They're very cost effective. It's a totally sealed and contained mixer. When you look at this mixer, there is nothing rotating inside of it. There's no parts. There's no, there's nothing inside there. It's an empty vessel. So it's totally sealed and contained. There's no mechanical components. Your bearings, your lubricants, your seals, all of those are removed from your powder. This is going to give you a long operating life. It's going to keep you from having breakdowns when you get, if you have abrasive powder, it would get your seal. You don't have to worry about any of that with this kind of mixer, and it's really an advantage. You also have low abrasion. You're really just lifting it up with friction against the wall and letting it fall down. So there's not really going to be any abrasion inside the mixer. One of the things that you can do to help is you can change the shape of the mixer to randomize the mix, or you can add baffles or agitators inside. And there, instead of, falling directly down, you might fall down and hit an angle or fall down and do something else. And it's really going to help to randomize the mix and give you a better quality of your mixture. So one of the things with tumble blenders is that they're not good for segregative powders. And we mentioned this at the beginning. Now this slide, I took this from a technical paper, but what it shows is it shows powders segregating over time. Now I should note in advance that this was done in a cylinder, and a cylinder is not really ideal for mixing. Normally tumble blenders take a more random shape, or a more, designed shape to add more randomness into the mixture, so you see a lot of cones or V shapes, and this was done in a cylinder, but it does show the segregation that can occur. And what happens is, you can see at 1 minute, it's mostly well mixed, but you can see a little bit of the gold beads coming out from the red beads. Now, what we have here is the gold beads are 1 millimeter, the red beads are 2 millimeter, and the blue beads are 0.6 millimeter. So as you rotate the tube, you can see that the gold beads start to come out. At 1.5 minutes, you can see the bands start to form. At 2 minutes, you can see the blue start to come out of the batch. And then at 5 minutes, you can see clearly defined bands where you have red powder in one portion of the batch, gold powder in another, blue in a third, and then you can see it actually forms a nice, very clear repeating pattern. So you can see that this powder, even though you are putting it into a rotating vessel and moving it around, really what you're doing is demixing the powders. And one thing is that even similar powders can segregate over time, and this is called overmixing. So what you can do is add your powders into your mixer and mix, and relatively quickly you can get a homogeneous mix. But then, say you want to get an even better mix, what can happen is you can keep rotating your blender and turning it over, and these particles will actually, because of the little changes in them, one might be a little bit bigger, or one might be a little bit higher bulk density, or different shape, they can actually move differently within the batch. And when they're moving differently, they can segregate over time. So some of the cons to tumble blenders. Really the only one, or the main one, is that they're only suitable for non-segregative powders. Other more minor details are that the feed and discharge must be connected for charging and discharging. So you need to, every time you put powder in, you have to open the vessel, connect the feed in, and then feed the powder, close up the vessel, mix. When you want to discharge, you then have to open the bottom and allow the powder to come out. So if you have something that's toxic or hazardous, or you don't want to be exposed to air, this can be a little bit of an issue. Another thing, and this is minor as well, well, not minor, but it should be noted, is that there's a safety concern. You have a large rotating vessel. You have to make sure that your personnel are clear of this vessel when it's in operation. Just standard safety procedures. In my opinion, the cons are minimal. If the tumble blender is suitable for your type of powder, it's a great choice. And that's why this is one of the dominant types of mixers in the powder industry. They really are used in a very wide amount of powders, processes, and they're very common. So moving on, we have ribbon blenders. Ribbon blenders are a convective style of blending. So what they're going to do is they're going to have a rotating ribbon inside the batch, and that's going to create those convection currents that we had discussed about earlier. So how they work is you have a trough, and that trough is going to be partially filled with powder. Normally it's filled, it's usually filled above the center line and then even slightly more above that, depending on how full you want to fill it. There are different guidelines for that, and you can always talk to a manufacturer about that. But what you're going to do is you're going to fill the powder, and then you're going to rotate that auger. That auger is going to move powders in two ways. It's going to move them around circular with the axis, around the radial, in a radial type of motion, around the center point within the batch, and then it's also going to move it horizontally within the batch. So you have two types of motion. You have radially and you have horizontally within the batch. I think this is hard to envision, so I like to think of it like a Rubik's Cube. You start out with the Rubik's Cube, and you have every face is identical. You then start rotating from the one end, and you start to randomize your mix. So you're rotating these cubes, and then you can then add the horizontal mixing element in, and you can envision it in your head how you're going to be then mixing the batch. So you're going to be taking portions from one and moving it to the bottom and then sliding it horizontally around. And normally, the ribbons are going to be doing both the horizontal and the radial movement, but I think it's easier to envision it if you break them up. So one of the best things about these blenders is that there's a large variety. So they come with a single shaft, they come with twin shafts, There are paddles available instead of ribbons. There's also ribbons and paddles available. In addition, you can do multiple ribbons, so if you want to try to move the powder more vigorously to speed up your mixing time, you can add multiple ribbons and that will help. So there's really a large variety within this mixture. There's different angles to generate different types of movement and different amounts of movement in different directions. So the pros to this type of blender is that you can get good mixing quality for products with a varying particle size and bulk density. So this goes back to the segregative powder. This blender is suitable for segregative powder. If you have a powder where you have multiple different particle sizes and multiple different bulk densities, you can then put this in this vessel, mix the powders, and you will get a product that is homogeneous. Another thing is you can get a wide variety. So these mixers are available in a wide variety of sizes, from very small to very large. They come in multiple shaft designs so that you can not only grow around a single agitator, but around multiple agitators. And that really, I think, helps these become more universally applicable. So you can, use them for more applications and shift from one application to another. So now on to the cons. One of the biggest cons is that the seals are submerged in the product for this design. So if you imagine the Tumble blender, you have totally sealed and your mechanical pieces are removed from the batch. For the ribbon blender, your seals are going to be submerged in that product during the blending. So what's going to happen is if you have a fine product, or if you have an abrasive product, or if you have a product, that you just likes to migrate into fine places or something like that, this product will find its way into your seals, and you can end up with issues. There are designs for seals, and there are different mechanical designs that can be utilized to help keep that from happening. But again, it's just something to consider. Another thing to consider is that they can be hard to empty. Normally, they are discharged through a central port in the bottom. You can see here this has a circular port, and here this has a larger port. What's going to happen is you put your product in, you mix it, you then want to discharge it, so you're going to open that port, and all the powder for that whole batch is going to have to come out that port right in the center. But you're going to have to move the powder from those outer corners into this batch, from the outer corners into the center of the batch for discharging. And that can sometimes leave bits of the powder behind in the corners of the mixer. There is another option, and that's bomb doors. So if you envision a World War II bomber where the bottom opens up and I guess they would drop the bombs out of. Well, here what you would have is you would have them along the bottom of your mixer, and they would open up, and you would drop the entire batch at once. What that's going to do is make it much easier to empty. One con to the bomb door is that you are then going to be transporting your powder in mass, and you're going to get segregation again. So you can have a perfectly mixed batch, discharge it via your bomb doors, and have it demix while it's being transported down into your hopper below. So now we'll move on to the conical screw blender. The conical screw blender is another convection style of blender. What it is it's a screw inside of a cone, and the screw rotates around the batch, and it's going to pull material up from the bottom. So what you do is you fill the material into the mixer, and you can see you want to fill not the entire vessel, but below the orbit arm so that it gets free movement around the batch. And here you can see the effective capacity is lower. The transport is going to be by the auger. So you're going to lift material up from the bottom and move it to the top. And then the auger is going to be rotating around. So you're going to be placing it at different portions on the top of that batch. You can see here that material is going onto the auger from all the different heights within the batch. So what's happening is that the auger is not a closed auger where all the material at the bottom ends up at the top. Material is free to enter and leave the auger the entire length of the auger. So as it moves up, you're going to be taking material from the bottom, and moving it up, but some might get off here, and some might come on here, and some might get off there, and as you work up, you can really pull powder from within the entire batch, and then you're also moving around the batch as well. So because it's transport by an auger, this is actually pretty easily understood, and I think it's interesting because you can calculate different things using the auger transport. So to calculate the transport capacity for an auger, you need the pitch, the diameter, and the screw speed. With that, you can calculate the pitch, but then above that, you have to remember that this is not a closed auger like a standard auger. This auger is open, so because of that, we add in a fudge factor we call the screw efficiency. What the screw efficiency does is says how much of the powder is actually being transported and how much is just getting on and off. So that's going to give you a fudge factor to your screw transport capacity. Moving from there, once you have the transport capacity and you know the volume of the mixer, you can then calculate the mixing time. But to do that, so you can say one time through the entire screw is going to be X amount of time. Well, that's not very useful because if you go take the entire batch and just mix it once, it might not actually be mixed. You might need to take that entire batch and move it a couple times up and down that screw to get the entire batch mixed. So that's the other fudge factor, and that's called the homogenization factor. So that's the amount of times or the number of times that the batch must be passed through the auger to give you a homogeneous batch. So what are the pros to a conical screw blender? You can have very high mixing quality. You get a full batch discharge, so because of the shape, you have a valve at the bottom. You open it, and gravity will carry all the powder down and out of the vessel, which can be very useful. The screw is cantilever for these units, so there's no bearing at the bottom. So there is no seals within the product. You can see here all the mechanical pieces are going to be above the powder, and that can help increase your uptime, increase your production time. They're flexible. You can often fill these anywhere between 100 and 15% of your fill volume, and that's going to give you a wide variety of products you can mix in this, because you can mix one at 1,000 liters, one at 500 liters, one at 200 liters, and use the same blender for all of those batches. Another advantage is that they're available in large sizes. We can go, or these units can be manufactured up to 100,000 liters, or about 3,500 cubic feet. So they're available in very large sizes, and again, that's because you're just going to be transporting with that screw up the batch. So it's possible to lift the material and move it around and transport it, because you're only transporting a portion of the batch at a time. One caveat with the large sizes is that the screw must be supported at the bottom, so you do lose some of the advantages of having the seals and bearings outside the product zone. So what are the cons to the conical screw blender? One of the cons is that if you have material that's sticky, it can bind to the screw. So the screw is going to be welded onto the shaft, and then you have a C along that weld, along the screw. If there's material that will bind, it will bind within there, and that can give you carryover from one batch to another, or just create an additional piece of equipment that someone has to clean, I guess. Normally, they have a higher cost than the ribbon or the tumble blender. You have the mechanical component of the orbital arm within the batch, and that normally increases the cost, above what a ribbon blender would be. The mixer height, these mixers are at a vertical configuration, so you normally add powder from the top and discharge it out the bottom, and you're going to have a vertical stack-up. That vertical stack-up can be a disadvantage in buildings where you have height restrictions. So, if you have a two-floor facility in which you need to do your blending, and you want a 5,000-liter blender, it could be a tight fit because you'd have to lift the material up to the top of the blender and then discharge it out. And it could be possible, but you'd have to consider the height of the mixer. Overall, they're a good choice for segregative powders, and they really do offer a lot of flexibility, and they offer the full discharge. So this is a comparison of the different types of mixers with the different types of blenders in a segregative powder. And, we've hit on this a couple times today, but tumble blenders are really not suitable for segregative powders, and I think this chart shows it well. What it is you have different size particles, and they have a size ratio, so you can have a 1-to-1 size ratio in which they would be equal, 2-to-1, 3-to-1, 4-to-1, 5-to-1, and so forth. And as you change the size ratio, one particle is getting much bigger than the other. You can see that at a low size ratio, the conical screw blender and the ribbon blender are both comparable to they're both better than the tumble blender, but they're comparable. All three give you very low standard deviation. As you change the size ratio, you can see that the V blender is going to give you much higher amounts of standard deviation. So you're going to see much more of one product than the other in your samples. And this is because you're having a batch that segregates within your mixture, and you're not really homogenizing thoroughly. You're homogeneous, but you're segregated in that some portions of your batch will have more of one powder and some will have more of another. And then as you continue to go out, you can see that the ribbon blender and the conical blender stay close, but as you get very, very disparate particle sizes, the conical screw blender can be slightly better. So, selecting the correct mixer. Often, tumble blenders are the default blender choice. If it's not suitable for the tumble blender, you should consider the other types of blender and choose based upon the pros and cons of the different designs. Another thing to stress is that you really should take your entire process into consideration. Consider what's upstream, what's downstream. Consider the height of your building. Consider if you're going to be doing multiple different batches. Consider, if you want to run different types of powders or anything along those lines, because all of that can be as important as kind of some of the mechanical aspects. Really every type of mixer can mix to a certain extent, and you just need to select the correct one for your process. And then I've discussed a couple different types of mixer today, but really there's a very wide variety of options of mixers out there. If you look at the left, this is a silo mixer. So what this mixer does is it's an auger that pulls material up through the center of the batch and then dispenses it at the top where it can diffuse down over the material. This is a plow shear mixer. So what this type of mixer does is these plows will plow through the product. It's normally used for pastes or more viscous materials. This is a planetary mixer. Planetary mixer, again, is normally used for pastes or other types of materials, but it can be used for powders as well. This is a Z-blade mixer. The Z-blade, it's just another type of configuration for the ribbon blender almost, but it's normally used for more viscous and more cohesive materials. And this final one is a vertical ribbon blender, where previously we discussed a horizontal ribbon blender. So here what you're doing is you're going to be lifting material up and letting it fall down within the batch, and that's going to be giving you your mixing.
Thank you, Chris. Now we'll begin our question and answer forum. As we're limited on time, we'll try to accommodate all of your questions, but apologize in advance if we're not able to answer all of them. If we're not able to address your question at this time, someone from Hosokawa will respond to you offline at a later date. Let's take a look at these questions here. All right, Chris, first question, let me read it here. I am blending two powders in 1 degrees rather easily. Which mixer would be most suitable?
Is that going to be shared? Do you want to share that? Okay. So if you have a powder that is going to be friable, if it's going to degrade easily, any of these mixers would really be suitable for it. The tumble blender, if you have particles that are equal size, if it's not segregative, then the tumble blender is definitely going to be the best choice for you. The ribbon blender would work as well. Sometimes you can get a little bit more force from the blender, and then the Nauta blender again or the conical screw blender again is going to be another option for you. So I would say that they're all suitable for friable powder.
Okay, next question, Chris. which mixer would be best suited for the addition of liquid to a powder blend?
So if you're going to be adding liquids to a powders, I would recommend using either the ribbon blender or the conical screw blender. You can use a tumble blender. So what happens is that you will add the liquid into the powder and it tends to form clumps. You can add a rotor to break up those clumps in a tumble blender, but it can sometimes be hard to evenly disperse those liquids amongst the powders. For the ribbon blender, what you can do is you can add the liquid in across the entire batch at once, and you can see, because the whole batch is in motion, you're going to get good homogenization and good dispersion. For the conical screw blender, you can add in, but you're going to want to be adding it in right in the mixing zone, so it's a little bit of a slower process, but it's maybe a little bit more controlled as you add it in.
Okay, let's take a look here.
Give us a second as we scroll through the questions.
Yeah, how about this one, Chris? How do you know? How does one know how materials are mixed? If materials are mixed thoroughly?
That's the most common question that we get from customers, and often it's a question that we need to give back to the customers. So it's to consider if your product is thoroughly mixed. What you should probably do is consider the sample size that you're looking at. So if you are going to be selling your product in very small samples, then you need to make sure that every portion of every material is within that small sample. And if you're mixing, and you're providing your product to your customer in very large samples, you need to make sure that every material or materials to the equivalent or the desired mixing ratio are within every portion. And I just repeated myself twice. I apologize. But the sample size makes a big difference. Once you have your sample size, then you can look at the actual analysis of your product. So you can look at and say, maybe the color's off in this portion, but it's good in another portion. Is that good because this or that will matter? It's really a tough question, and it's often one that we have to rely on the customers to provide, chemical analysis, color analysis for the samples.
Okay, let's take a look here. Let me read the next question. Chris, what type of mixer would you recommend for blending two non-free-flowing powders?
So if you're looking at non-free-flowing powders, I'm going to try to switch through the slides. Give me a second here. So for non-free-flowing powders, you can look back up here at the go back, all the way to the beginning. You can look at the mixer selection chart. So if you have non-cohesive powders, you're going to be looking at either a mid-shear, high-shear, or impact mixer. And then from there, you can kind of narrow it down based on the need. So if you have particles that are very cohesive, you might need to go for an impact mixer or a high-shear mixer. If you have particles that are cohesive but only mildly cohesive, then you might be able to go for a mid-shear mixer. So it really can depend on the cohesiveness of your powders and how easily you think you're going to be able to, break those cohesive parts apart and then, disperse them amongst the other powders.
How about this question here, Chris? With regard to post-mixing using a conical mixer, are there any recommendations on discharge?
So for discharge of the conical mixer, we just put manufacturers, put a valve on the bottom. It does not really make a difference whether you have the screw turning or not. You can discharge and the material will slide out of the mixer or discharge by gravity.
Next question. How do mixing times compare between the three mixers presented?
For the three mixers, you're going to get pretty comparable mixing times. For the tumble blender and the ribbon blender, you're going to have the entire batch in motion at once. And because the entire batch is in motion, you're going to be doing more transporting. Because you're going to be doing more transporting, you're going to get a faster mixing time. The conical screw blender will be slower, but it will be able to do the mixing for you as well.
Next question. All low-shear mixers Is it true that all low-shear mixes would not work for cohesive powders?
It's a difficult question, and it's hard to answer. Some powders can be mixed in low-shear mixers, especially once you start to look at the convective mixers, because you have a more forceful movement within the batch. You can mix powders that are going to be more mildly cohesive. So often, if you have a powder that's, like wet sand would very well be able to mix within either the ribbon blender or the conical screw blender, because you're going to be able to, via the agitation within the batches, naturally break it apart. For the tumble blender, it's a little bit harder, but again, sometimes maybe they can include, internal elements within the batch to help provide a little bit more agitation to break it up.
Okay, let's take a look at the questions. Next question. For calculation of mixing time, how would you consider the fact that the material is very hygroscopic with the calculation of mixing time?
So for the calculation of the mixing time and looking at the hygroscopity, what that's going to do is that's going to affect the freedom of the powder. So when you look at the screw and how it's transporting, the material up, if you have a product where it's hygroscopic and maybe has a little bit more cohesiveness, what can happen is that you're going to get less material entering and exiting the flake. So you can have a lot of the material kind of getting on the screw and not much getting off until it gets to the top. So what that's going to do is that's going to increase your screw efficiency. But so it's, that might affect your mixing in other ways too, because you have less material entering and exiting the screw at different heights within the batch, which are also going to be helping to mix your material. So, having a screw efficiency that varies, it's kind of that calculation can be used to help you figure out how much time it's going to take or what your screw volume is, but screw volume does not exactly pertain to mixing efficiency in a direct comparison.
Okay, next question. For well-mixed cohesive blends, would it segregate?
So we did not discuss that cohesive blends, but it tends to be that a non-cohesive blend will not segregate. So I believe that's called a stable mixture. So once you generate the mixture of a cohesive powder, you can pretty much do what you want with it, and it's not whatever you want with it, but you can handle it more than you would a free-flowing powder mixture, and you're going to get less breaking up of your powders or less segregation of your powders.
Chris, next question. Have you ever run the conical mixer in reverse?
So that is a good question, but it's something that you wouldn't want to do. The powder would then be pushed down into the bottom of the batch, and you're going to compress the powder, which is non-compressible, and you're going to damage your mixer. Sometimes it can be used to help push material out of the mixer, but it's not common, and it's probably not often recommended. Gravity is normally enough for exiting.
Okay, let's keep scrolling through these questions here. Is there an optimal amount of time that is recommended to let blends settle before further use?
Normally, I would say no. So you have to, if you're using a blender and you have very fine particles that would get entrained in air and you want to let them settle, possibly yes. But normally, once the mixing is done, the mixture is set as long as it's stationary. And so those powders should be right away able to be dispensed.
Okay, next question. If a liquid is added to a conical blender, will the powder level need to be at max, or would the liquid spray work on at a reduced batch, like half a batch, for example?
It really depends on the liquid addition mechanism. So it's trickier because for the conical screw blender, the liquid is normally added right to the conical screw portion rather than onto the static batch. So if you were to say add it evenly across the top of the batch, you have to imagine that a large portion of that batch is not in motion, which is part of the pro of that kind of mixer. But you're spraying it there, you're going to get liquid added to a certain portion in excess, and it's going to clump. So you're only going to add to the portion right near the screw. If you reduce the level within the batch, what you're going to be doing is adding liquid kind of up in this area, but your powder is going to be down here. So you're going to be adding it, it's going to be hitting the wall, and then falling down. So you're not going to be dispersing it as evenly.
Okay. Next question, Chris. Is it possible to provide conditioned air to or through a conical screw blender or other type of blender to control moisture in the mix?
That's a good question, and it is possible. Often you can percolate air through the batch if you wanted to remove moisture or strip something out, or just to, to help the batch flow. I mean, the question here pertains particularly to controlling moisture, and the answer to that, I guess, is yes, it can be done. You can also purge these mixers. They're all closed vessels, so you can get them in airtight designs for all the different ones discussed, and then you can purge them before and after every batch, and they'll work for anyone.
All right, Chris, I think we're just going to leave it with one more question, but what it seems to be the most common question, more or less, is in line with clients seem to be asking the question, which is the best mixer for my application? That seems to be the most common question here. Whether it's for starch or other food product or a chemical, that seems to be the most common question here.
So for particular mixes, there is no real best answer. If there was a best answer for what is the best type of mixer, then this presentation would have only included one type of mixer, and we would have only discussed that. Really, what you have to do is consider the entire process of what you want to do. So consider all of the things that you want to mix together. Consider the particle size, the bulk density. Consider if you have mixing ratios. So say you have 1% of one and you want to mix it in with 99% of another. One trick you can do is mix that 1% with 9% to kind of disperse it amongst the other one, and then mix that 10% in with the other 90%, and that can sometimes help you, to more efficiently mix. So there's some tricks and there's some things that you can do to kind of help you with your mixing, but really there is no best mix. And even some mixing applications, you can have your particle can be at one size, or your particle can be at another size or another size. So really you have to consider each mixing application on their own merit.
Thanks, Chris. We at Hosokawa Micron Powder Systems sincerely thank you for your time and attention today. Please refer to our website, hmicronpowder.com, to view past educational webinars as well as a schedule for upcoming webinars. If you have any further questions or requests, you may contact Chris Paulsworth, and his contact information will be displayed here. So if you don't mind going to the last slide there, Chris. And one other note, this presentation will be posted on our website. So if you know of any colleagues who may be interested in viewing this, or for that matter, prior webinars, they may do so by accessing our website. Again, we thank you and have a good day.